And see, I told you, right? The more this introduces phase shift, whereas this does not introduce the phase shift. That's why it is non-inverting, and this is called as inverting terminal. Fine. And most of the amplifiers require the symmetrical supply. This is symmetrical supply means what? If you apply 6 volts here, the minus 6 volts should be applied here. If you apply plus 15 here, this has to be minus 15 here. Okay, that is why they call it as symmetrical supply. Plus 15, minus 15, minus 6, plus 6. The range could be from plus or minus 6 volts to plus or minus 15 volts. Okay, and the very famous or the very popularly used amplifier is mu A741. Mu A741. And for mu A741, we apply plus 12 volts and minus 12 volts. Understand? So mu A74 is one amplifier. There are many such amplifiers. It's not the only amplifier, but in the lab, in the laboratories, the amplifier that we use in our college and in most of the places, it's mu A741. Unless otherwise specified, OpAmp means it is mu A741. That standard is mu A741. Okay, so very popularly used OpAmp, and for that OpAmp, the supply is plus 12 and minus 12. And since here, whatever the positive voltage that I apply, the same negative voltage needs to be applied here at the negative supply. Okay, that's why they say they require the symmetric supply. It will not so happen that you will apply 10 volts here and you will apply minus 12 volts here. No, that will not happen in most of the cases. Okay, so it is plus or minus 12 or plus or minus 15 or plus or minus 6. Okay, that is what they mean by symmetrical supply. Okay, I hope you have understood that. Now, see here, this explains us the power supply connections. Power supply connection. I told you, right? It has got a dual power supply. From the dual power supply, we have 3 knobs like this. One knob is, if it is mu A741, it is plus 12, okay, volts, and this is minus 12 volts. And what did I say about this? This is ground.
Grounding.
Okay, and sometimes this ground is, see, they are calling this ground as common 0 volts rail. So the voltage here is 0 volt. Understand that? See here, this is connected to this, okay, and this is connected to this. No, positive. The positive, see here, this is positive. This is positive of the battery. Where is it? Where is it? Yeah. Here, this is positive is connected to here, plus 12, negative is connected to this minus. They say they are showing it differently. See, this has to be positive because the positive supply is coming here, and this has to be negative. Fine. You need not have to copy down this particular figure. Okay. Anyways, I'll be providing you with the notes that is there in that. Okay. So this positive of this is being connected to this. Okay. Then the other point, then there is ground. Without this ground, you cannot what have this plus volts and minus volts being applied. So this is common. This is common to all. Whichever connections you make, okay, so that connections you're making with respect to this. Is that okay with you? So positive comes here, negative comes here, and in between you have ground, that is this. This is common. That is what they are showing. Instead of showing one, they are showing it two. So whether you show the output supply or the supply as this or this, it's the same. So let's not bother much about this. Why they have shown two such symbols here. Okay, so you can use one or you can use two, not a problem. Understand that? But without this ground connected, okay, you cannot apply these two, is what they're saying. Is that okay with you? Fine. Enough. That is what is the supply connections that we are having. Okay, now we shall see the OpAmp parameters. Okay, so there are different parameters that we have to understand as far as the OpAmp is considered. Okay, and it's very similar to something that we already have discussed regarding the amplifier. We have discussed what is open loop gain. What is open loop gain? Can anybody tell me now? What is open loop gain? Open loop gain is the gain with or without feedback. Just tell me that.
Without feedback.
It's without feedback. Okay, so open loop gain is gain without feedback. Now, can you tell me which among the two, open loop gain or closed loop gain, is greater?
Open loop gain is greater.
Open loop gain is greater. So, what do we do to bring that open loop gain down?
Negative, give the negative feedback.
We apply negative feedback. So that is what is being discussed here. There is not much being discussed, but you can just see the notations that they are using. Open loop gain, if they say, they'll say AOL. Okay, V naught by V in. Since it is the what voltage gain, it is voltages we are taking. Closed loop gain, ACL. Okay, this again is V naught by V in, but this V in is after the feedback is employed. Okay, to understand that here no feedback circuit, here you have feedback circuit. Okay, and one more thing that we should understand is AOL is very much greater than ACL. Understand that? Okay, so this is very whatever that we have discussed with amplifiers, apply the same for OpAmp also. Understand that? Now they have given us a problem. See here, an operational amplifier operating with negative feedback produces an output of 2 volt when supplied with an input of 400 microvolts. Determine the value of closed loop voltage gain. Now, can you do this now? Okay. Tell me what is this 2 volts? 2 volts is input or output? That's output very clearly specified. So this is V out is 2 volts. V in they've given as 400 microvolts. So with V naught and V in given, they are asking us what is the closed loop voltage gain. Okay, and how can we find out whether it is open loop voltage gain or closed loop voltage gain? It is always output voltage by input voltage, output voltage by input voltage. Understand that? So, how much would this be? You just give me that. How much would that be? So, they're asking us what is closed loop voltage gain, that is ACL, and it's given by output divided by input. How much is this? Input is 400 into 10 power minus 6. Can you give me this number? Anybody? You're not calculating that? No? Or yes? Anybody?
5,000.
5,000.
Okay. So the closed loop gain is 5,000. Okay. But this closed loop gain would be much lesser if you see. But since the input is very small, okay, the gain is large. Okay, and this is what we get our closed loop gain to be. Understand that? And see here, the V in is 400 micro and V naught is 2 volts. So that means what is happening to the input and output? By the time input comes to the output, okay, it increases or decreases?
Increases.
It is increasing. So that means since it is an amplifier that happens here, OpAmp will amplify the signal. That's why 400 microvolts is becoming 2 volts. So if 400 microvolts has to be becoming 2 volts, what should be the gain? The gain of the amplifier should be 5000 is what is the meaning of that. Okay. So the input increases and becomes 2 volts. From 400 micros, it becomes 2. Understand that? And why is that increase? It is increasing because it is getting amplified. And why it is getting amplified? Because it is output of an amplifier. Is that fine with you? Now, this is another OpAmp parameter. So if you understand all these parameters, you will understand when would be a OpAmp called as a good OpAmp or an efficient OpAmp. Understand? Or for a good OpAmp or for an ideal OpAmp, okay, what should be its parameters? Fine. So that is why this understanding these parameters would help. So this input resistance, this also we have already discussed. What is this input resistance? Input resistance of an amplifier is defined as the ratio of the input voltage to the input current expressed in ohms. Quite simple, as we have seen earlier. This is ohms. The input resistance of an amplifier is very much dependent on the semiconductor technology employed. Okay. In practice, values range from 2 mega ohms for common bipolar types to over 1112 ohms for FET and CMOS. FET means field effect transistor. CMOS means complementary metal oxide semiconductor transistor. They're all transistors. Here, FET and CMOS are different technologies to build a transistor. They're all simply transistors. Okay. So for different types of transistors, different that means transistors means this using these transistors only we can build amplifiers. Understand? And the input resistance would rather depend on all this. Okay. Let me show you where the input resistance would be. See here. This is where you have to see your input resistance. This is an OpAmp. I'm not writing the power supplies. Let me not write that for simplicity here. This is, what is it? Okay. And this is where you have your RI. Okay. And they're saying that this input resistance has to be very large for an OpAmp. The input resistance of an operational amplifier is defined as the ratio of the voltage, input voltage to input current. And this should be large. This should be very large for an OpAmp. Okay. Or we can say it should be ideally infinite. Understand that? See here how much large it is? 2 mega ohms. Understand that it would be ranging till there. That means it's quite big. Understand that? So the input, that means it is the resistance which is there between the inverting and non-inverting terminal. This has to be very big for the OpAmp. Understand that? And what is that? It is the ratio of input voltage and input current. Fine. So that is what you're saying. Anyways, the output is here. Is that okay with you? Just understand that input resistance is ratio of V in by I in, and it has to be very large, which means that ideally it has to be infinite. Just that. Okay. Then comes this output resistance of an OpAmp. Okay. So as we have seen earlier during the amplifiers, here also the output resistance is defined as the ratio of the open circuit output voltage to short circuit output current. What is open circuit output voltage? Here, everybody. So if we have an OpAmp or an amplifier like this, what did we say? These are input terminals. These are output terminals. Okay. So this is V out when open circuit, when the output circuits are open circuit. This is V out OC. This is an amplifier, mind you, in general. This is V out OC. Okay. What is I out SE, take the same amplifier. Okay, we're not dealing with the input now. In this output terminals, short this. Then you will find I out SE, short circuit current. Okay, so it's the ratio of output voltage when the open circuit output voltage to the short circuit output current. Understand? That is your R out. Fine. And how that looks like, you can just write it like this. So this is how your R naught would be there within. It's all internal. The input resistance, output resistance that we are telling, they're all internals. Internal. So this is A VI. Why this R naught has to be very small? If this R naught is small, whole of this AV in would come here as AV in. So for this here, for this to come as AV in at the output, R naught has to be very small. Okay, so understand that this has to be very small. Okay, and ideally, what should this be? If something is very small, practically, ideally, what is this? Can you comment? If something
0.
is very small, practically, ideally, it has to be 0.
0.
Good. It is 0, ideally, if it is very small. If it is very large, ideally, we call that has to be infinity. Is that clear to you? Why it has to be very small? See, this is what is the internal structure looks like, internal diagram of an op-amp looks like. Okay, and along with this resistance, there is this voltage gain into V in. V in is where V in is the voltage that we apply here. Plus minus. Okay, so that into A should be the output. Why? Gain is always V naught by V in. So what is V naught? V naught is gain into input. So if your output has to be gain into input, then R naught has to be really, really small. Okay, that is what is output resistance all about. And it would be in the range 10 ohms to around 100 ohms. What was the input resistance here? 20 mega ohms. Okay, where is mega and where are hundreds? Understand that? So 10 ohm to around 100 ohms. So that small would be your output resistance for an operational amplifier. Is that okay with you? Now, the next parameter, that is input offset voltage. This is a very important parameter as far as the op-amp is concerned. Okay, now let's understand this input offset voltage. Now, everybody see here. This is plus Vs, the positive supply voltage. This is minus Vs, the negative supply voltage to energize this particular op-amp. Then we have denoted the non-inverting terminal input as V2 and the inverting terminal input as V1. And this is the output. And one should, to understand this input offset voltage, you have to understand how the output looks like if the input is applied like this. If V2 is applied at non-inverting terminal and if V1 is applied at inverting terminal, what should your V0 be looking like is the question. Okay, so if you understand that, then understanding input offset voltage would be much easier. So this is how we do that. What we do is this. Everybody just see. The op-amp amplifies the difference of the input signal, and hence it is called as differential amplifier. The op-amp is also called as differential amplifier. It is also called, it's not differential output, but it is also called differential amplifier. Why it has to be called as differential amplifier? Because it amplifies the difference between the inputs. That's why it is called as differential amplifier. Is that okay with you? The op-amp is also called as operational amplifier because it performs so many operations like addition, subtraction, multiplication, division, integration, differentiation. That's why it is called as operational. But the same op-amp is also called as differential amplifier because it amplifies the difference between the inputs. Okay, so that is what is shown here. The difference, the output V naught, which is the amplification of the difference in input, okay, is given by gain A into V2 minus V1. Let's not bother as of now whether it is closed loop gain, open loop gain. Let's not bother. Okay, in general, what is output? Output is gain into input. What is input? Input is difference of the inputs. So what is difference of the inputs? It is V2 minus V1. Why it is not V1 minus V2? Can you just make out why it is not supposed to be V1 minus V2? That is because, see here, V2 is applied to the non-inverting terminal and V1 is applied to the inverting terminal. So the voltage applied to the inverting terminal has to be negative and the one that is applied at positive terminal has to be positive. That's why it is V2 minus V1. So this is what is the output is given as, where V is the output of the op-amp, V1 is inverting input and V2 is the non-inverting input. Fine. Now, when V1, V2 are same, let me tell you now. When V1 and V2 are same, can you tell me what is V naught going to be here? You can just comment on that. When V1 and V2 are same, what is supposed to be your V naught? Go on, make it fast.
0.
It has to be 0. Okay.
Yes.
Yeah. Ideally, I say ideally now. Ideally, okay, the op-amp output should be 0 if V1 and V2 are same because it is actually amplifying the difference between V2 and V1. But practically what happens? Practically, this V naught would not be 0, though, yeah, practically, V naught would not be equal to 0, though V1 is equal to V2. Understand that? There will be very small output which would be there in the output terminal, though V1 and V1 and V2 are same. Ideally, if V1 and V2 are same, V0 has to be 0. Ideally. Okay. Ideally, it should be 0. But practically, it would not be 0, though V1 and V2 are same. This is because, okay, imperfect internal balance, they say. Due to imperfect, so why it is so? If somebody asks you, you should say imperfect internal balance, or sometimes it is maybe due to the noise also. Okay, or noise at the input. Okay, but in practice, due to imperfect internal balance or noise at the input, there may be some voltage present at the output. So that means there is some non-zero voltage. Understand that? So that is not good. Is that understood? That non-zero voltage which is coming, okay, is not good. Ideally, it should be 0, or practically it should be very small. Practically it is there. We cannot make it 0, means at least try make it very small so that it is very near to 0. Understand that? So for that, we apply some voltage to the input terminals. Understand? The voltage that must be applied to the operational amplifier input in order to make the output voltage exactly 0 is known as the input offset voltage. The input is non-zero, so the input that we apply, this is additional input, I mean. The input that is applied to these input terminals, externally. Okay, to make this V naught 0 is called as what? Input offset voltage. Fine. How can we apply this input offset voltage here? Input offset voltage may be minimized by applying relatively large amounts of negative feedback. This we can do by this, they are telling, by employing negative feedback, okay, or by using offset null facility. In the OpAmp, there is a pin. I told you 8 pins, right? Among 8 pins, there is one pin which can be used for making this offset, this in non-zero output as 0. Okay, and that is called as offset null pin. So that is called as offset null facility. So using these two, we can minimize this B naught. Okay, in AC coupling amplifiers, offset voltage is not a problem and can be ignored. In AC coupling, it's not at all a problem, just saying. So this input offset voltage that we need to apply to make the output 0 when the inputs are same, okay, is not a problem for AC coupling amplifiers, because it just we just consider AC, whereas in DC coupling we consider AC and DC. That is when this problem comes. Understand? But as long as the AC coupling amplifiers are used, you need not have to be bothered about this input offset voltage. It will be taken care of automatically. Is that understood? So this is what input offset voltage is. Anything you have to ask me regarding this? Yes or no? Okay, no problem. Now, uh, now let's move on with the next set of parameters. Full power bandwidth. Full power bandwidth. The full power bandwidth is another parameter. Is equivalent to range of frequencies at which the maximum distorted peak voltage falls to 0.707 times the maximum value. So this full power bandwidth to just understand. And typical full power bandwidth range would be 10 kilohertz to 1 megahertz. It's a bandwidth. It's a range of frequencies. Fine. And what is that full power bandwidth? The full power bandwidth is same. You have the frequency response like this. You come down by 3 dB. Okay. Then you have F1 here and F2 here. Okay. So this is maximum voltage, or V max, you say. This is V max, and this would be 0.707 times the maximum V max. Okay. And this range is referred to as full power bandwidth they're saying. This is not of much importance. Okay. And they have not given much information regarding this also. Fine. So just understand it is just this. Okay. Full power bandwidth of an amplifier is equivalent to the range of frequencies at which the peak undistorted means with no noise. Okay. The peak undistorted peak value falls to 0.707 times its maximum. That is here. They are called as, okay, the full power bandwidths. Fine. Now let's move on to slew rate. This is very, very, very important. Okay, the very important parameter. Let's now understand. Have you heard about slew rate? Slew rate actually talks about the speed of the device. Okay, first understand this input and output here. Okay, what is this input? This input is called as step input. It is like steps here. It starts at -1 and goes to +1. Fine. Now I'll ask you a question. What is the time that this input is taking to go from -1 to +1? X-axis is time. Can anybody comment on that? Can anybody comment on that? What is the time that this input voltage V in is taking to go from -1 to +1 at this point? What time is it taking? It is taking no time. It is taking no time. Okay. But ideally it is fine, but practically it will not be so. But let's assume that it is going to -1, it is going to +1 from -1 at this point. Okay, and that point is this, the same point. But in output voltage, what happens? In output voltage, to go from -1 to +1, or this gets amplified, let's say, because this is an op-amp, right? Operation amplifier. This gets amplified, and after getting amplified, the -1 would +1 would grow to the maximum. The maximum that is possible is plus Vs and minus. What is plus Vs and minus Vs? You've seen this, right? These are the inputs. Okay, so here you have plus Vs, and here you have minus Vs, the negative and positive power supplies. So the maximum that the op-amp output can reach is these two. Okay, so from -1 it reaches minus Vs, from +1 it reaches plus Vs. That is what is the output. But see the time it is taking to go from my negative to the positive. So it is not suddenly going from negative to positive as happened here in the input, but it is taking some time to go from negative to positive. Understand? So that is what slew rate talks about. The slew rate of an amplifier is the rate of change of output voltage with time in, okay, with time in response to a perfect step input as shown in figure. What is it? Rate of change of output voltage. Rate of change of output voltage. With time, we need not have to say. This is optional. Actually, you can just leave that. Rate of change of voltage means it's change of voltage with respect to time. So slew rate is that. What is slew rate? Slew rate is rate of change of voltage. Okay, rate of change of voltage means variation of voltage with respect to time. Small variation, very small variation in voltage V naught with respect to time is what is slew rate. Okay, here slew rate delta V naught by V out by delta T. Delta V out by delta T. What is this? This is V out. This is V out waveform. Fine. Here, slew rate for an op-amp should be high for reducing the delays. That means if this is high, that means if slew rate is high, rate of change of voltage is faster, is what they're saying. If the slew rate is high, rate of change of voltage is faster. So that means here, this can happen. So with some slew rate, this is what is with some given slew rate, this is what is the output. Okay, if the slew rate is increased, okay, the output could be this. So which is better, the red one or black one? Which is better, the red one or black one? Anybody, can you make out? As far as speed is concerned, taking speed into consideration, can you tell me red one is better or black one is better?
Red one.
Red one is better. What? How red one is better? It is taking lesser time to go from minus Vs to plus Vs, whereas this black line is taking more time to go from minus Vs to plus Vs. So if rate of change of voltage is high, so if slew rate is high, it means that the rate of change of voltage is fast. Rate of change of voltage is fast means it takes less time to go from minus Vs to plus Vs. Understand? So if it takes less time to go from minus Vs to plus Vs, okay, it is faster. The device is faster. Understand? So for a faster device, this slew rate has to be high, is what it is saying. Understand that? And it is typical values ranges from 0.2 volts per microseconds to 20 volts per microsecond. These are the typical values of that.